A Cornell University graduate student was staring at a plot of data one afternoon when she noticed something that shouldn't have been there. A faint line, barely above the noise floor of the instrument. She actually second-guessed her own eyes before she trusted what she was looking at. What she'd found was a sound, a real, continuous, physically measurable sound, humming out of the emptiness of interstellar space, 14 billion miles from Earth, being picked up by a spacecraft that launched during the disco era. And nobody had ever heard anything quite like it before. Everybody, this is the story of Voyager 1, listening to something no human instrument had ever detected in the history of space exploration, a persistent, monotone hum coming from the space between the stars themselves, not a metaphor, not a sonification added for a press release, an actual signal recorded by an actual instrument that scientists are still working to fully explain. Let's start with the instrument responsible for this discovery, because most people have heard of Voyager 1's cameras and its golden record, but almost nobody knows about the piece of hardware that's actually still doing science work right now, 50 years after launch. Voyager 1 carries something called a plasma wave system, sometimes called the plasma wave subsystem, built around two thin antennas that extend about 10 meters, roughly 30 feet, out behind the spacecraft in a wide V-shape. This instrument was never designed to pick up sound in the way a microphone does. There is no air in space for sound waves to travel through the way they do on Earth. What the plasma wave system actually detects are oscillations in plasma, the ionized gas of charged particles that fills the space between stars. When those charged particles get disturbed, their electrons vibrate at specific frequencies. The tighter those electrons are packed together, meaning the denser the plasma is, the higher the pitch of that vibration. Scientists can convert those electrical oscillations into an audio frequency and, quite literally, listen to what the density of interstellar space actually sounds like. For years after Voyager 1 crossed into interstellar space in August 2012, becoming the first human-made object in history to leave the direct influence of our sun, the plasma wave system mostly picked up occasional, dramatic events. Every so often, an eruption on the sun would send a shock wave rippling outward through the solar system, eventually slamming into the thin interstellar plasma surrounding Voyager 1 and triggering a brief, detectable oscillation, almost like a bell being struck once and left to ring. Scientists used those isolated events to estimate the density of the interstellar medium around the spacecraft, but it was sporadic by nature. You needed the sun to cooperate. You needed a solar event powerful enough to reach that far, then you had to wait for it to actually arrive, sometimes over a year later, and hope the signal was clean enough to measure. That's where Stella Koch-Ocker comes in. As a doctoral candidate in astronomy at Cornell University, working alongside Cornell research scientist Shami Chatterjee and Professor James Cordes, Ocker began digging through years of raw Voyager 1 data, looking specifically at what was happening between those big, dramatic solar shockwave events, the quiet stretches nobody had paid close attention to before. That's when she found it. A signal buried in data collected between 2017 and 2020. Incredibly faint, only a few times stronger than the background sensitivity limit of the instrument itself, but present. Consistently present, not tied to any solar event, not appearing and disappearing the way the shockwave signals did, just there, steadily, month after month, for the entire 3-year stretch she examined. Ocker described the moment of discovery herself, and it's the kind of detail that makes real scientific breakthroughs feel a lot less like movie moments, and a lot more like what they actually are: careful, patient, slightly uncertain work. She said she was literally just staring at a plot and thought she saw something really faint, and found herself wondering if she was starting to see things that weren't actually there. She wasn't. What she'd found turned out to be a completely new kind of signal, one nobody had specifically gone looking for, hiding in data that had already been collected and sitting there, waiting for someone to notice it. The team published their findings in May 2021 in the journal Nature Astronomy, describing what they called a persistent, weak, essentially continuous plasma wave emission, humming along at a frequency of roughly 3 kilohertz, low enough that, when converted to an audible tone, it produces a single, thin, almost eerie note. Ocker described the character of the sound in her own words. She said it's very faint and monotone, because it sits within a narrow frequency bandwidth, and confirmed plainly that what the team was detecting was the faint, persistent hum of interstellar gas. Here's why that description, faint and monotone, actually undersells how significant this discovery was. Every previous measurement of the interstellar medium's density around Voyager 1 had depended entirely on those intermittent solar shockwave events, meaning scientists effectively had scattered snapshots separated by long gaps of total silence, sometimes over a year apart. This new signal changed that completely. Because it was present continuously, rather than triggered by an outside event, it gave researchers something they'd never had access to before. A running, ongoing measurement of interstellar plasma density that didn't require waiting around for the sun to send out a detectable pulse. Cornell research scientist Shami Chatterjee explained exactly what that meant for the team going forward. He said they'd never had the chance to properly evaluate it before, and now they knew they didn't need a fortuitous, sun-related event to measure interstellar plasma at all. Regardless of what the sun happens to be doing on any given day, Voyager keeps sending back detail. Think about what that actually represents. A 50-year-old spacecraft built with less onboard computing power than a modern digital wristwatch effectively upgraded the entire methodology scientists use to study the region of space just beyond our solar system, not through some dramatic new instrument, but because a graduate student went back and looked more carefully at data that had already been sitting in an archive. Ocker and her team also noticed something else worth paying attention to. The hum wasn't perfectly static. Over time, its precise frequency drifted slightly higher and lower, and that movement wasn't random noise. It directly tracked changes in the density of the plasma around the spacecraft as Voyager 1 continued moving deeper into interstellar space. When one of those older dramatic solar shockwave events did occur during the study period, the persistent hum's tone would rise and fall right along with it, confirming that this quiet, continuous signal and the older, well-understood shockwave signals were describing the exact same physical environment, just at completely different volumes and completely different timescales. Ocker put it simply. She said it's virtually a single tone, and that over time, they could hear it change, with the way the frequency moved around telling them how the density itself was changing. If a story like this, real recorded data turned into something you can actually hear, is exactly the kind of space science you come here for, subscribe now, because there's a lot more still unfolding in the years since this discovery was first made. So what's actually producing this sound in the first place? Even now, years after the initial discovery, that question isn't fully settled. Ocker and her colleagues have proposed that the persistent hum likely comes from something called thermally excited plasma oscillations, combined with quasi-thermal noise, essentially the natural, low-level jittering of electrons in interstellar plasma caused simply by the ambient temperature of the gas itself, rather than any single dramatic triggering event. In other words, interstellar space isn't perfectly silent and empty the way most of us picture it. It's filled with an incredibly thin haze of charged particles that are constantly gently vibrating on their own, all the time, everywhere. And Voyager 1 just happened to be equipped with an instrument sensitive enough and now positioned in exactly the right place to actually pick that vibration up. There's a genuinely poetic detail buried in all of this that's easy to miss if you're only skimming the headlines. Voyager 1 carries something called the Golden Record, a phonograph disc bolted to its exterior containing greetings in dozens of languages, music from across human history and culture, and recorded sounds of earth, birdsong, thunder, ocean waves, all assembled under the direction of the late Cornell astronomer Carl Sagan, meant as a message to any intelligent life that might someday intercept the spacecraft drifting silently through the galaxy. That record was built specifically to carry the sound of our world outward into the void. Decades later, in a strange kind of symmetry, a different Cornell University team is now using that very same spacecraft to listen backward, capturing the actual ambient hum of the space between the stars and bringing that sound home to us instead. Voyager 1 didn't just carry Earth's voice outward, it became humanity's first working microphone dropped into the space between star systems. The scientific value of this discovery goes well beyond simply being a novelty you can put headphones on and listen to. Understanding the precise continuous density of the interstellar medium matters for far bigger questions in astrophysics. That density profile helps researchers understand how our solar system's heliosphere, the vast protective bubble of solar wind and magnetic field the sun projects around itself, gets shaped and pushed around by the pressure of the interstellar material surrounding it from the outside. It also feeds directly into models of how stars form, since the same interstellar medium Voyager 1 is now sampling directly as the raw material that eventually collapses under gravity to form entirely new stars elsewhere in the galaxy. Even our basic understanding of where our solar system actually sits structurally within the wider galactic neighborhood depends on getting an accurate read on the density and turbulence of the material immediately surrounding us. A single faint hum, detected by accident in an old dataset, connects directly to some of the largest unanswered questions in modern astronomy. And this story hasn't stopped since that first 2021 announcement. Ocker herself, now firmly established as part of the ongoing Voyager science team, has continued studying the signal in the years since, working to build an actual physical model that can properly explain not just that the hum exists, but precisely why it behaves the way it does as Voyager 1 continues its journey. She's been candid about how much is still unknown. In her own words, the team has some ideas about how much farther Voyager will need to travel before its instruments start sampling what she called more purely interstellar waters, meaning plasma less influenced by any lingering solar effects and more representative of true, undiluted interstellar space. But she's also been honest that nobody is entirely sure exactly when Voyager 1 will reach that point. The spacecraft is still, in a very real sense, in a transitional zone, close enough to our solar system that the sun's influence hasn't completely faded from the data, but far enough into true interstellar space that this genuinely new kind of signal was there to be found in the first place. Here's what makes this discovery even more remarkable when you place it in the context of where Voyager 1 stands today, in 2026. Of the 10 original science instruments Voyager 1 launched with in 1977, the vast majority have been deliberately powered down over the decades, sacrificed one by one as the spacecraft's plutonium power source has slowly, steadily decayed in a careful, long-planned effort by NASA's engineering team to keep the mission alive as long as physically possible. Today, Voyager 1 operates with only 2 functioning science instruments left. One measures magnetic fields, the other is the very same plasma wave system responsible for this discovery, the instrument that first caught Stella Koch-Ocker's attention on a plot that almost looked like nothing at all, out of everything this spacecraft was ever capable of measuring. The tool that first let humanity hear the sound of interstellar space is one of the last 2 pieces of scientific hardware still doing its job, right now, this very moment, 14 billion miles away, and getting farther every single second. That's genuinely worth sitting with for a moment. A spacecraft built before most of the people reading this were born, running on technology that predates the personal computer, using an instrument nobody specifically designed to detect a continuous background hum, ended up capturing something no scientist had ever recorded before, simply because a graduate student took the time to look closely at data that had already been collected and largely set aside. Space isn't the silent, empty void most of us grew up picturing. It has a voice, a faint one, a patient one, and for over a decade now, humanity has had exactly one working set of ears out there positioned to actually hear it. If you want to keep following this story as Ocker and her colleagues continue refining their model of exactly what's producing this signal, and as Voyager 1 keeps pushing deeper into truer and truer interstellar space, subscribe and turn on notifications, because this spacecraft is still listening right now and will be here the moment the next piece of this mystery gets solved.